This presentation discusses the design of a sonification developed for a specific field in exosolar astronomy related to planet hunting. My name is Michael Quinton, and I have been researching the application of sonification with exosolar planetary data. I am currently conducting research on the application of sonification in relation to sports tracking apps. I am researching the use of virtual reality for live musical performance. This presentation is about the use of sonification in the application of astronomy, specifically related to planet hunting within an asteroid belt situated in the Beta Pictoris exosolar system. The study was conducted with an astronomer who volunteered to participate and will be referred to as AB, a female in her 30s who has been an astronomer for some time. AB was interested in using sonification in her work to see if it could help her to detect a planet that was possibly orbiting around the asteroid belt, causing a number of asteroid collisions, which over time created a wave in the belt system and altering its shape. The dataset was a simulation that was built from data collected from the Beta Pictoris system, and further information was added that replicate the development of this exosolar system over a long period of time. The temporal aspect of the data spanned over 1 million days. The second column represents the horizontal plane of the asteroid belt, or the x-axis, measured in astronomical units. The third column represents the vertical plane, or y-axis, measured in astronomical units. And the fourth column details the asteroid's collision data and the sizes of the collisions. An interview was conducted with AB, and she was asked about the data and its parameters. Grounded theory was used to analyze the information gathered from the interview. Keywords related to descriptions of the data emerged. AB described the asteroids as being made of ice and rock. She described the sound of colliding asteroids as ice cracking or boulders falling. AB also described the asteroid collisions and how these are probably caused by the movement of a planet. The gravitational influence of the planet as it spins on its own axis causes asteroids to be pushed out of the way and into each other. Over time, the planet's gravitational influence causes the asteroid belt to warp. Rather than remaining flat, the belt's disk changes and becomes a spiral-like formation. These descriptions were then used as the basis of the sound design. AB described the dataset as an object with dimensions. Here we can point to the idea of replicating the asteroid collisions as sound events related to the interaction of sound objects. Sound perception is based on impressions of dimensions of space, volume, significance, proportion, material, and time. To construct a sound object, then the sound designer needs to make use of the various psychoacoustic properties working in relation to each other to convey the proportions, qualities, and temporal spatial behavior which is being conveyed in the data. Rather than simply using one or two parameter mappings for sonification, multiple mappings are used to sculpt the sound and give it a more realistic and tangible quality. We can see how all the psychoacoustic properties indicated in the slide work in relation to each other. If we imagine the asteroid belt as a circular ring moving around the parent star, then this would point towards the use of surround sound to replicate the spatial movement of the planet as it moves along the asteroid belt. The belt is full of asteroids of different sizes, and when they crash into each other, they have different levels of impact, which can be represented using pitch, timbre, and amplitude combined. The asteroids collide at different points along the asteroid belt, and spatial parameter mapping is used to indicate the coordinates of where these collisions took place. This data could possibly reveal the presence of a planet which is causing these collisions as it passes through the asteroid belt system. These four psychoacoustic properties work together to convey impressions of size, magnitude, and movement, since the changes in spectral qualities of the sound convey size and impact. The sound design aims to create something similar to ice breaking or rocks colliding, but with enhanced pitch to make it easier for the user to hear distinctions. The spatial perception must also authentically replicate the asteroid belt as it is captured from Earth. It takes the perspective of a telescope viewing the Beta Pictoris system, which is seen at a distance as a flat representation which envelopes the parent star. In this instance, stereo sound representation is used. In this slide, we're going to hear an example of the sonification played back at a speed of 5 milliseconds. During the testing, only 30,000 lines of data were sonified. This was due to the limitation that exists in Cycling 74 Max, where only 30,000 lines can be uploaded. This portion of the data covered 30,000 days in the life of the asteroid belt of the Beta Pictoris system. Sonification was mapped so that larger asteroids were represented by lower pitch and smaller collisions by higher pitch. One can also hear the spatial representation of where the asteroid collisions occurred across the stereo field. This gave a representation of collisions happening within the asteroid belt as if it is being observed from a telescope. AB referred to the familiarity of the soundscape. She could also associate to it and follow how the data work within these parameters. This familiarization aroused strong mental images of what AB was hearing. She described the sonification sounding like breaking ice and also sounding like raindrops on a rooftop. AB had a sense of being able to see the asteroid belt and hear the planet moving through it. AB could convey quantities such as size, hearing the different sizes of the asteroid collisions quite clearly due to the changes in the psychoacoustic properties. She could also follow the orbit of the planet clearly and track its movement through the asteroid belt. AB could also get a sense of the speed of the planet's orbit within the system. The sonification clearly indicated a sense of regularity with the asteroid collisions, which clearly indicated the presence of a planet causing these collisions to occur. The planet could be tracked over time due to immediate recognition of a pattern of activity within the asteroid belt. Regularity in the occurrence of asteroid collisions is rhythmical, making planet detection fast and easy. The mappings were able to convey the data as objects consisting of dimensions of size, speed, and motion quite accurately. Sonification also helped to present a temporal spatial aspect that was not immediately perceivable when using visual methods, especially in relation to the speed of the planetary orbit. Spatial mapping played an important role in the sonification design. It seemed to be an effective mapping for astronomical data due to its temporal or spectral nature. It seems to be the gluing element that solidifies the relationship between all the other psychoacoustic mappings in conjunction to each other. The conclusions that can be drawn from this study are that the use of familiarity in sound design helped AB to make strong associations between the data and the sonification. Spatial mapping was important at conveying the aspects of time, dimension, spatial orientation, and association. Sound object replication enhanced the user's ability to recognize the size of the asteroids and the impact when colliding with each other. This allowed AB to get a rough impression of quantities. By combining all the multiple mappings together to create the sound object, AB was able to use the sonification as a replacement of the 3D visualization and numerical data. Future work would consist of testing the sonification with other astronomers who work in the same field of astronomy to measure consistency of the design method. Further development of spatial mapping could augment temporal spatial qualities and intensify proportions and dimensions of sound objects. It would also be of use to test these sonification design methods in other areas of application. Thank you for your attention.